Happy to present the work called Loop Transformers are better at learning algorithms. And this is a joint work with my great club advisors, Garg, Rob, and Dimitri. Let's get started. So in this work, we're trying to focus on this problem, which is we want to teach transformer to solve the linear regression problem. And I want to first tell a bit about how the setup work. Because I think maybe some of you are now very familiar with this. So let's say for linear function, we have this parameter W, which is a d-dimensional vector. And we have each xi's, which are the data for the linear function that also comes from RD. And during training, we sample the W and xi from a standard Gaussian distribution. And then we calculate yi, which is the output, the label for the linear functions. And then we'll train a randomly initialized decoder transformers such that we're given this format. So the prompt will be structured as we have x1, y1, x2, y2, all coming from the same linear functions. But each xi are randomly sampled. And then because this is a decoder transformer, it has this causality noise attention, such that when it's saying x1, it only has the information after x1, and it's trying to predict y1. And when it's saying x1, y1, x2, it's trying to predict y2, so on and so forth. So with this, we have a efficient way that given this n pair k pair input is trying to predict k pair output at the same time. And then we're training on the objective of minimize the MSE error between the predicted y's from the transformers and the true y's. And with this training signal, we will train this decoder transformer to teach it to learn the linear regression problem. And also, I want to just a bit more clear about the setting. So a lot of work with trying to solve like math problem with transformer, some of them are trying to make it by tokenize it as the tokens and then map to the transformers. But here, what we're dealing with the case is that we'll treat every xy's as the real numbers. We will not tokenize them. We will not do all the like which thing as which, but we just put it into a linear projection to map it from the d-dimensional problem dimension to the embedding dimensions. And then we just treat these as the embeddings and put the transformers. And in the end, we do another projection, project it back to the output space. And also just to be clear, because xi are d-dimension, yi are one dimension, when we're passing it to the linear layer, we'll pad each yi with a zero padding to make sure they have the same dimension. So this is the settings. I hope everyone is clear with it. And okay. Right. So because going back here, we have each xi from RD and yi will be a real value. That's why. Okay. So we have this question: can we teach a transformer to solve the linear regression problem? And there's already a work from the Stanford group, which I cited here, Garg et al. They're showing that when you train with the objective and take the randomly initialized transformers, you're able to train the transformer to almost perfectly solve this linear regression problem. What does it mean? So if you look at the right figures, they're showing, so the problem dimension they're focusing on is 20. And they're showing when you're varying the in-context examples, what is the predicted y's performance compared to the true y's, and they're measuring with MSE error. So we know that when problem dimension is 20, if you have less than 20 examples, you will be in energy determinant system, and then you can solve as good as the ordinary square solutions. But when you are over 20 examples, you can solve perfectly with the least square solutions. And so the orange curve is the least square solutions, like this. And the blue curve is transformers, like the trained transformers. So we can see that it is matching the trend with the least square solutions. And in the end, if you zoom in, it has the approximation error of around 1e-3, 1e-4. So it's not perfect as these first solutions, but it's also kind of trying to approximate the solution as good as it can. So that is the literature. And so after seeing this, people have the question of what is transformer doing when it's trying to solve this linear regression problem? And we know there is a least square solver, which we will do the calculation of x transpose x inverse x transpose y. And maybe we're thinking transformer is just learning approximation to this solution. And then there's an interesting question like, do we have other ways to solve the linear regression problem? And maybe we can solve it with an iterative algorithm instead, where, for example, gradient descent will just iteratively update this WT with the calculation that only involving matrix multiplications, but there's no matrix inverse in it. But we know that we have this transform architecture here, where each layer they're having the free learnable parameters. So we know that if we don't have like actual force on the training, they will not naturally have this repeat like same shared weights across layers. So it will not do this iterative algorithms naturally if we just train on the objective we just mentioned. So the question is, can we utilize a variant of transformer to emulate these iterative algorithms? And the solution we're proposing is, let's just loop the transformer up. By looping, we mean that we're just having a single looped block or a single transformer layer. And then we pass this like multiple times, sharing the weights again and again until the output. And we call this looped transformers. So just to summarize, I just talk about the problem setup and what is the motivation for our work. We want to solve the linear regression problem. So primarily in the remaining, I'll just focus on problem dimension 20. And we have this prompt in this format where we have xi pairs sending to the transformers, and it's a decoder transformer, so we will get these outputs or predicted outputs. And standard transformers will be able to solve this with 12 layers transformer, as the previous work shows. And we're hypothesis that is learning a closed form solution of this ordinary square solutions. But we're proposing to use a loop transformer where it only have one layer of learnable parameters. And we're thinking it is a similar, like it is trying to emulate a iterative algorithm. So, question?
Yeah, the first question is I'm not clear why zero padding or why. Like if you use the common equalizer like GP2 or Llama, then there is no need to the padding because every number will be converted by the or you create a completely new equalizer.
Yeah, so the good question. So the question was why we need zero padding for the Ys. And the thing here is we're not taking a pre-trained tokenizer or anything. So this linear projection, you can think of it as the tokenizer. Like we're not treating the number as number where we separate with each tokenizer and then put it to a already learned embedding table, but we just treat x1 as a real value and we'll pass it to a linear layer. Linear layer will map it from this xi dimension small d to the embedding dimension. So there's no, like, all of the things are trained from scratch. There's no thing from any of the pre-training models.
Yeah, then I ask this model is it's only used for this regression problem and cannot others, and that's mathematics. And I guess for the decoder there is the same, using the linear projection to project it for a real value.
You can hear?
Yeah.
Yes. So yeah, so, these are all
the main space is continuous, right? Which is different from natural language here. Line space.
Yes, exactly. We're focusing on this continuous space or like regression problem instead of a classification problem.
Yeah, another question is your loop transformer. I'm wondering, it's more like a digital connection like that, or you really like, you can set how many times the looking all operation.
Could you maybe explain a bit more?
Yeah, like you have a loop to transformer, like, by definition, do you need to define how many times we need to have this loop operation?
Yeah, so I will talk about it later. We have a hyperparameter to set the maximum loop iterations during the training. Yeah.
Okay, so in your next slide, you transform into transformer to the traditional solver to take the matrix inverse. So my naive question is like the traditional solver solve the W type in one shot. Why is transforming to transformer with layers?
Okay.
The iterative one has to transformation.
Okay, so that's a good question. The question is why we need 12 layers to mimic this traditional solver, which is a one-shot expression where for loop transformer, we have one layer of transformer, but it's iteratively emulating this. So I think Angelique is expert in this. There's a previous paper also from Angelique, which says that if you want to express some like operation of matrix or something, you need how many layers of transformers? Like for this matrix inverse, you need a lot of layer of transformer compared to matrix multiplication. So that's why approximately you need more layers to emulate this. But for matrix multiplication, it will be a simpler operation compared to inverse. That's why it is able to be expressed by fewer layers.
The problem is the inverse is very expensive.
Yes.
Oh, another question. So, we know that you can use one layer to perform gradient descent, right? Oh, no,
Okay.
yeah, you are using this to perform gradient descent, and you use this iterative algorithm to perform like multiple iterations of gradient descent. But then why do we need this residual connection?
So you're talking about this. Okay, so I will talk about this later. Why we have this residual connection. And yes, so I mean, the one layer for gradient descent is kind of another paper which talks about the expressivity of the one layer transformer, that the best it can do is gradient descent. But we're not focusing on that aspect because like we're not training a one layer transformer directly, we're training the looped transformers. So it's kind of different. Yeah. Thank you. Okay, so just to give you a bit highlight on what is the result of the loop transformer before going into all the details of it. So on the right-hand side, I have the same figure I just showed you for the standard transformers. We're varying the in-context examples. We're measuring the MSE loss between the predicted Y's and the true Y's. And so there's a hiding curve behind that's this white curve, that's the least square solutions. And the dashed blue curve is the transformers. We're showing it's matching, almost matching the optimal solver we have. And then the loop transformer is the red curve, which you can see it's having the almost same performance as the transformers. So it's showing as good performance as the standard vanilla transformers. And on the right-hand side, I'm also showing another figure that's related to Moo's question, where during training, we have this dashed line indicating the trained loop iteration you encounter, which in this case is around 13 loop iterations. And then during inference, we take this loop transformers and then loop it up to 100 times. And we can see that this loop iteration of this loop transformer is able to find a fixed point solution, like quote unquote emulated fixed point solution, where it will converge and stay at this solution you find at maybe 30 loop iterations. Yeah. Question?
So my follow-up question is like, which one, the loop one or the not loop one, but the traditional transformer one, which one is expensive? Because the traditional transformer, I think they only need 12 layers.
Mhm.
But for the loop, you do like over 20 iterations and just, and then you convert.
Yeah, so I will talk about it later. I have a actually comparison between these. Yeah, like a trade-off between the time and storage and stuff. Yeah. Sarah?
How do you come up with the 12 number?
Ah, okay. So the 12 number is I just taken from the previous work.
So they have run experiments for like all from like one layer to say.
Okay, I get your point. So the question is why we think 12 layer transformer is a good enough solver for this problem. So basically, I'm not sure if they have run like different number of layers. Throughout their work, they just use 12 layer transformers, which works well. But later in our work, we also showed like try a different number of layers for the vanilla transformers. And basically for linear regression, it is, I think around like 10, 8-ish layers, you will solve it
Okay,
as
so
good
it
as
could
well.
have been as small as an 8-layer transformer rather than a 12.
Yeah, but it will not be as good as one layer.
One layer loop.
Yeah, like if you compare the number of parameters, learnable parameters.
Yeah, so I
yeah.
understand that the loop transfer is more, weight, the parameter shape.
Yeah, it's parameter efficient, yeah.
If we expand the loop transformer and copy one layer, 100 layers, then those are equivalent.
Yes, you're talking about the effective depth of the loop transformer.
Yes.
Yes.
Let's treat a 100 layer transformer, but each layer has identical weights. That
Yes.
is good. Yeah.
Yes, you can think of it like, yeah, in that way.
Yes.
Okay, thank you for all the great questions. I will start trying to talk about the training algorithms and stuff. Okay, so let's get started. We have this figure just shown. We have this prompt to the transformer and they have this output. And just to mention that every time during the training step, we will randomly sample this piece. So there is not a fixed data set for these prompts. And every time it will be generated randomly on the fly. So transformer will not likely to see two identical prompts during the training. That's just how they design their training algorithm from the previous work. We just follow it. And we will just denote the MSE error, the error to be MSE error between the predicted Y's and the true Y's. And yeah, as we mentioned, we have this loop transformer. We will denote the number of loop iterations as B. And also we have this additional word is called residual connections here. And so when we're expanding it, what that means is we will start from a 0 embeddings. And every time we'll have this prompt adding to this embeddings, and then pass it to one loop transformer block and get one output. And then we repeat this process B times. And yeah, so that's how like the loop transformer format does. And during the training, we take the loss where we only take the last T loop iterations output to try to match it with the ground truth Y. So there's an actual parameter called T, which is the loop window size. The reason for that is we're just sort of trying to getting help from the previous literature on RNN, what are the recurrent network, where if you take the gradients up to the very first loop, you will likely get some like gradient vanishing stuff or anything. And it's also very costly in the computation memory stuff. So instead, we will truncate this, like we just borrowed an idea from truncated back propagation through time, where we only take the last T loop iterations output and trying to match it with the ground truth Y. So this will be our last signal for the loop transformer training. And just to demonstrate what does that mean, we take the figure we just had from the previous slides. Let's say this is the these loop iterations, and it has a window size of T. So effectively, when we're training, we're trying to minimize the loss within this range to make it as small as possible. But before that, it will just be whatever it is doing. Okay, so that.
What is the window size?
So in the training, I usually use t equals to 5 or 10 or 15, depend on the task. But yeah, it's a hyperparameter tutoring. It will be less than b, of course.
So this essentially means that for every window you calculate loss, training loss separately, then back up to that portion.
So the grading will be only taken in this window.
But then you are not, then how are you updating the first based on the early loops? Let's say you had like 100 loops, right?
Mhm.
And you were doing a loop of window size 5.
Uh-huh.
So you take my understanding is that you take the loss of only last 5 windows,
Last 5 loop iteration output.
last 5 iterations of to calculate the loss.
Uh-huh. But the last signal also will affect the weights. It is just, yeah.
So only for those 5 you will update it, or you will update it for the full? No, it's actually the same set of weights.
Yeah, it's the same set of weights. And actually, there's a tiny training details. So there's 2 ways to train when you have this window size. One is you have a kind of like scheduling on the window size where you start with training over here, like you're moving your window size along your training. Does it make sense? Or the other way is you just keep your window size at this position where you have your max loop iteration, and you just take the t previous step out. So yeah.
So this is for each loop, you're separately taking the loss, or is it like?
So
Trying to understand is,
mhm.
are you disregarding the signal for the early first 95 loops,
Yes,
and you are not updating based on that?
no, not updating this. Yeah. So yeah, as I mentioned, there are 2 ways. So I think one of the concerns you have is there's also meaningful signals from the previous loop output. Why don't we take loss for that? The disadvantage is, of course, if we take throughout the whole loop iteration, that means 100 loop, let's say 100 loop iteration, it will take a lot of memory during the training. So this way is just kind of as efficient, like it's a more efficient way, but it is doing as good as if you take the whole loop, loss on the whole loop iteration output. That's one way to think about it. And the other way is that, as I just mentioned, there's a scheduling in the loop window. Like during training, we can either fix, like just take the loop output from here and take the last signal, or we switch, like we're starting from the loop window here and then slightly switch it until to reach the maximum B loop iteration. So I'm actually, like I'm making the details here, but during the training, I'm doing this scheduling of this window. And there's just, there's a tiny difference of doing the scheduling and not doing the scheduling in one task I observed. The other tasks, they're all same. So yeah.
So you're moving which loop iterations you're going to take the loss from.
Yes. Like, yeah.
And I don't know if it's a lot quickly, but you might not have to spend a lot of memory to actually store them. Because technically they are just activations. You just need to store partial derivatives, right? And they could be summed up. You don't have to keep it full. Like it's equivalent. It's like think of it like as a batch of
I see.
Mathematically.
Yeah, I think I didn't really like explore the way of efficient implementation of this. I just, yeah, just take a very naive way of tracking the loss. Yeah. But thanks.
Yeah, I have a very simple question, like for next iteration or next loop, like how will you deal with the output from previous layer? Because this work is claimed as loop transformation, do we need to care about the output from the previous layer? Like do you do an addition or do you have to discard the output?
What do you mean output from?
Like
this?
yeah, no, like you have a class mark.
Yes.
Yeah.
So you need this.
Yeah, do you do the addition here?
Yeah, plus means addition.
Addition and at output, you only request the value corresponding to the current time step.
Uh-huh. I mean, you mean this is
Yeah,
the
yeah.
current time step? Yeah,
Because that's a bit counter intuitive because the input is not a exactly matching the actual input. It's accumulating the output from previous steps.
are you talking about size mismatch between this and this?
I think there is a distribution in that. Because I'm thinking about how to make sure that the term you are adding from previous layers of data, how will matter how meaningful it is.
So we have to have this input from previous layer because this is a looped transformer. We're looping to make sure the output from previous layer will be fitting to the next loop iteration.
It's just latent.
Yeah, so the thing is, the vanilla, like, when you think about loop transformer or like wait time transformer, there will not be this P in this addition.
Yeah.
So just think like you have output and then passing to next input. The only thing we are adding here is this P, and I will talk about why we're adding it here later. But yeah, the only difference is we have this P added to the embeddings.
Yeah, this made me feel like the architecture is exactly the same as our in the sense that for each kind of iteration, you use the transformer there instead of LSTM cell.
I mean, similar, like, I mean, all of the current models are kind of, yeah, like, are you talking about this or are you talking about this?
Yeah, I'm talking about like this whole process is exactly the same at our natural language processing where the input to a cell is both the latent vector from previous time step and the current and the input current time step.
Okay.
Like in the same basically it's exactly the same.
I see. Okay, yeah, I agree that this is like this is very similar to the previous recurrent network. Yeah, like there might be like maybe you need the projection here, you need some state here, but yeah,
That's right.
yeah, it's similar. Yeah. Okay. All right. So now I'm going to talk about two key factors that will make what happens. So make the loop transformer converge or stay at this solution it finds after it is passing the loop iteration it trained on. Okay, so figure will be more helpful in explaining. So let's say we have the loop iteration, it is trained up to this iteration B's. And then we're measuring the test error when we're inferencing this loop transformers, and it may pass this loop iterations. So this comes to our previous question of why we have this addition here, we call it input injection, which basically we observe that if we don't have this input injection, means we don't always have a signal from the raw input. Then during the inference, if we have more loop iterations applied to the loop transformer, it will have this diverged behavior where it will just go into a random solutions. But if we have this input injections in the architecture, then it will find this loop curve where after the train loop iteration, it will stays here. So that's basically the reason we have this input injections. And another key factor is the value of B or loop iteration we set during the training. So we also see that depending on the task, let's say we have this example where if you're training on a smaller number of B, you will likely during inference having a diverged behavior after the train loop iterations. And if you have a reasonable number of B, you will find a fixed point solution after the train loop iteration. And also the thing is, if you increase your B after this maybe let's say 20 is enough, but you increase it, then the loop transformer will always try to find the fixed point solution before the train loop iterations. But if you see the curve, you can see that maybe it is like if you call this is a algorithm, the algorithm converges slower compared to the algorithm found by this curve. But so there's kind of a trade-off, but the value of B is important, where smaller B will result in a diverged curve like this. And we will always find a fixed point solution before the train B's.
Is input injection the same as like a residual connection in a normal transformer?
So yeah, so good question. We know in normal transformer there is input injection. Oh, sorry, residual connections. This is the actual extra input injections. So residual connections normally means like after this transformer block, you pass in the input of the transformer block to the output.
Yeah.
But this is you pass the very beginning, the prompt
Oh,
to the
Oh.
embeddings. So that's a slight difference, but you can think of it as a residual connection if you want.
and the prompt is the same for every iteration.
Every loop iteration, you always pass in the same prompt embedding. Yes.
But you still have scheme of the prompts for different timestamp.
What do you mean masking?
I mean, masking the prompts. For different step, with different chain of the-
Are you talking about the causal map masking of the decoder transformer?
Yeah.
So the causal masking will happen in the attention layer, but input, you're just passing the full information. There is no masking there.
I was just wondering, any thoughts, so they think like, or similar. Artists, they like just sort of assume if you have like an infinite number of loops, you can like solve a fixed point equation, like numerically, and sort of train that. I feel like, I guess anything sort of similar here that you could do like with the transformer thing.
Could you maybe repeat?
Yeah, so like, I guess there's something similar with like an RNet type of architecture where you like loop it, and like, I guess if you have like an infinite number of those loops, like, you know, it goes to a fixed point.
Mhm.
So instead of actually like iterating through it, you just solve, or the fixed point is solved based on like the layer parameters.
Okay. So I think you're talking about the literature of deep equilibrium models.
Oh, yeah.
Yeah, so when I was doing this, I also heavily tried on the deep equilibrium models. The thing is, they need to have a black box solver for the equilibrium states. And it is kind of, like I personally didn't find it very useful. Like oftentimes I couldn't find an accurate equilibrium state. Maybe I'm not tuning the methods enough, but I find this way is more of a simpler and naive and also work methods. So I just choose to, but I do understand this is very similar to the equilibrium models. It's just that we're not solving it with a black box equilibrium solver where you need to train the solver to solve it, but we're just explicitly train it with a like looped iteration signals stuff. Yeah. Okay, yeah. Thanks. So I will go ahead. And okay, so now let's talk about some experimental results. And sorry, I think I missed some questions in the chat. Oh. Yeah. So experimental results. We just shown that on linear regression, it works. This was the first figure I was showing you. Basically, when I say in distribution, I mean like during the inference, you will sample a new W and new set of X, Ys, but it's from in the same distribution. So that's what I mean by in distribution. So when we do this, it will be able to like matching almost perfectly at the transformer, and it is able to find a approximated fixed point solutions. And we're now showing some auto distribution setting because we wonder what is the solver the loop transformer is finding. Like, is it actually doing a gradient descent or some sort of iterative algorithm, or what is that? So we tried on the distribution settings where in this case, we trained on a linear regression, but we tested on noisy linear regression. And for least squares, which is the red curve, we know that when we're trained on, so basically when you use least squares to solve noisy linear regression, you have this double descent curve where during approximately at problem dimension 20, you will have this shoot up on the arrow and then it decreases. And then for the transformers, which is the blue line, and also the loop transformers, they also have the similar trend where it will have a ascent on the problem dimension 20 and then descent afterwards. But you can see there's slight difference where the peak you have from the transformer is here. And for the other loop transformer is getting smaller and smaller peak. So it looks to me very much like a ridge regression models, but yeah, it's just kind of a hypothesis that loop transformer, maybe because of its fewer number of parameters, it is preferring some simpler solutions. Sarah?
How do you add noise?
I just add noise to the, okay, I mean, y's. So y equals to W transpose X plus a noise.
So Y is, okay. And what kind of noise?
Gaussian. And I think the scale is like 0.1 or something, but I don't remember. Yeah. Okay, so there's another out of distribution setting where, so basically this is to see whether if we scale on the input during inference. Just to remind you, during training, we have X sampling from Gaussian, standard Gaussian. But during inference, we will take the X sample from standard Gaussian, but then just time spread, make it the range larger so that the range will never be seen during the training. And then basically least square did a perfect job here as usual because it's just solving the problem. And then all the transformers were the transformers having this degrading in this performance, where transformer is slightly like degrading up to like 5, but then the loop transformer are just shoot up to like random solutions. So in this case, loop transformer is not so good in doing other distribution setting, but also, I mean, transformer is not so good as well. They're just trying to approximate the solution in distribution. So that's like the two cases to show that it has some implicit bias to the solver it finds, but it is not learning the real solver, actually. And also, okay, now comes the trade-off between the loop and vanilla transformer, like what is the time trade-off, what is the memory trade-off? First of all, just to emphasize, we have the parameter efficiency. We're just using 1 layer of transformer compared to the vanilla transformer, they're using 12 layers. And then for the training efficiency, because we have this B, which is the loop iterations, we need to unroll B times. So the effective depth is B. So unrolling B times, meaning we need to spend this much of time in the forwarding pass. And here is a figure we have in the paper for the linear regression. What is the B during the training that during inference, like what is the performance of the different B's? So we can see that for the linear regression, if we set B equals to 12, which is the vanilla transformers using the previous work, it will not finding a, I mean, find maybe a fixed point solution, but not very good. And then for 20, it will shoot up to some random solutions. And only with like 30, 40, 50, it will stay at this place. So what it means is if we want to find such a loop transformer that find this kind of good fixed point solutions, we cannot employ a B with 12 or even 20. We need to increase the B to maybe 30. So this will increase the forwarding time, and that is the downside of using a loop transformer, where you need to spend longer time, like larger B, in order for the loop transformer to learn a meaningful fixed point solutions. Since
So how many parameters 1 layer transformer?
okay, so I remember 12 layer transformer use 9 million parameters. So divide by 12, that's the loop transformer parameters.
So during test time, you don't actually do like 20 plus, forward passes, right? Or,
I mean, if you, so during test time, I mean, you at least needs to reach the B loop
so
iteration.
you do enough loops to reach the accuracy that you want.
Uh-huh.
Oh,
Yeah, I mean, I cannot, like, let's say we train up to here, but we only inference up to here, then it's an awful performance.
and like the transformer itself doesn't like decide when to stop, right?
Right, yeah, we don't have a automatic stopping criterion in this case, we just set a predefined loop iterations during the inference.
Sorry, what is the legend?
Yeah, sorry, the legend is the value of B. The B is the loop iterations we set during the training.
Oh, so what is the x-axis? It is loop iteration during the.
So yeah, so the x-axis is the loop iteration during the inference.
Oh,
So let's say we train the loop transformer with the loop iteration B, and then during inference, we infer up to 200 loop iteration.
Mm.
What is the performance?
I'm curious whether you have tested how does the number of loop iterations related to the scale of the linear coefficient of the kind of thing, like what kind of parameters in linear regression affect the final selection of loop iteration?
Yeah, so that's a good point. I roughly touched it in some slides later, but yeah, thank you. Okay, so yeah, so that was the memory blah blah efficiency. Now it's sample efficiency. I will just try to quickly go through it. Because recall during the training, we randomly sample the prompts every time on the fly. So there's infinitely number of prompts or functions seen during the training. But let's have this question, like how many distinct prompts you need in order to train the transformer to a reasonable performance? And how is that compared to transformer and loop transformer? So we vary the distinct number of prompts during the training. So basically we generate a fixed data set with either like this number of distinct prompts and then just train on the data sets. And we can see that the loop transformer, the red curve, when you have fewer number of distinct prompts, it has better performance compared to the standard vanilla transformers. So this will largely be because loop transformer has fewer number of parameters, but that's one advantage of using a loop transformer, where if you have limited number of distinct prompts, loop transformer will give you better performance. And then during inference, as we just mentioned, like touched on briefly, during inference, loop transformer needs to be set to reach at least B number of loop iterations or even more. And what is the performance if you do a transformer but with different layers? So previously, we also always talk about 12 layers, but let's say if we have a 2-layer transformer, how does it perform? That is the green line over here. So that is already doing a very decent job. But if we look at a loop transformer, which is the yellow curve, when you loop 2 times, it is up here, like it is almost like a random thing. So with that said, during inference, if you compare the effective depth of the loop transformer and the standard transformer, like what is the performance you can achieve, then loop transformer is also not so effective in this case. Meaning that you need more loop iteration in order to match even a 2-layer vanilla transformer when you train it on the linear regression task. Okay, so that's like the trade-offs. And now I'm going to investigate other function classes. We just talk about, we're talking about linear functions, but we have other function classes also to investigate. Like one is sparse linear regression. So all of these cases, we keep the problem dimension to be 20. Input dimension 20, output dimension 1. And sparse linear regression, it is just linear regression, but we set the non-zero weights to be 3. Like every time we randomly choose 3 weights and set it to be non-zero. And the decision tree, it is a randomly initialized binary decision tree with step 4 and a 2-layer linear network where input dimension 20, hidden dimension 100, output dimension 1. And the weights are also Gaussian randomly initialized. More details you can refer to the paper, so I will just skip this part. So, okay, this part is briefly related to the question Chen had. For each different function class, we investigate what is the number of B you need during the training. And we just show for each one of the class, what is the performance. So let's look at in detail. First is the linear regression, sparse linear regression. We know they're just very similar linear regression tasks, only one of these is fewer number of non-zero weights. But we can see that for linear regression, you will need maybe 30 or more loop iterations to find a converged fixed point solution. But for sparse linear regression, you need 20 or more loop iterations to find a fixed point solution. So there's a difference of what is the value of B you need for this linear function class. And I think it roughly like have a loose connection to the how difficult this function class is to the transformer. And also another interesting thing is here, like we know two-layer random neural networks very hard to solve for us. But for transformer, when we are trying to fit the XYs from this two-layer random neural network, even we loop with set B equals to 12, meaning that's the same effective depth as the vanilla transformer, it is still able to find this fixed point solution as good as 20, 30, 40, 50-ish. So this is kind of weird in the sense that for us, we have closed form solution for linear regression. We need to tune the hyperparameter for lasso to solve sparse linear regression. We don't have a good way to solve two-layer random neural network, except like gradient descent or anything. But for transformers, the value of B they need to find a optimal like fixed point solution is different, and they have some relation here. So we'll just say, let's say the optimal value of B will be the smallest ones that enable the loop transformer to find this fixed point solution. I mean, this is also beneficial for the training where you have smaller memories and faster forwarding times and stuff. So we have this hypothesis or the hunch, like we don't know how to answer, but maybe the optimal value is an indicator of the task difficulty to the transformer when it's trying to solve this function class. But that's just hypothesis, like I don't have a good answer for that.
Quick question. So before, so that motivation of the loop transformer is for performing gradient descent. Have you ever visualized the loss surface of those functions and then visualize the path of the output of the loop transformer at each loop iteration?
Yeah, so we actually try to visualize in like 2D settings where it's easy to see, but it is not like a gradient descent or I mean, it's sort of like a momentum, but it's also not very likely. So we don't have a good idea of, I mean, we think still it is approximation to some solver, but it cannot be directly mapping to any of the iterative algorithm we know. Yeah. Thank you. And also this slide is just a proof of concept that for standard blue line is the standard transformer, red line is the loop transformer we train. We have investigate 3 function class, and in all of those loop transformer will either viewed as standard transformer or better than standard transformer, slightly better than standard transformer. So with that, I conclude my talk. Hope to leave you with the impression that we have a loop transformer that we train to emulate the fixed point solutions. With that, it's able to emulate this fixed point iterative algorithm within the training distribution. And also loop transformer can achieve same or better performance than vanilla transformer while utilizing only a small number of parameters. And with that, I conclude my talk. Thank you very much for coming, and I'm happy to take questions.
So you talk about fixed point solution. Fixed point of what? Which operator?
Yeah, that's a good question.
The gradient descent operator? Fixed point of that.
We were just trying to show that it converged to something, like when you have more iteration applied of like one function repeatedly applied, it pick the solution, but there's no like fixed point, like, yeah, we don't know what's fixed point of what, or.
The two-legged neural network, what's the weight of the networks at training and at testing? So are they all randomly initialized for the two-legged neural network?
You mean for this?
Not the two-legged.
Sorry, okay, yeah, this one.
Yeah,
Yeah, they're all randomly initialized from Gaussian.
and it's the same distribution at training and test.
It's the same. All these are in distribution tests. Yeah.
Another question, so you have studied how different function classes affect the number of loop iterations. Have you tried similar experiments on the vanilla transformer, like how many layers is needed to solve those tasks?
Okay.
I'm wondering if there is any connection.
Okay, good question. We didn't try. I think only varying number of transformer layers for the linear regression, not for the others. Yeah, but so far we only know 12 layers will excel in every case, but we don't know. Yeah, I mean, the previous work, they used 12 layers for everything, and that's what they're showing here. But yeah, we don't know how small the transformer can be to solve different function class.
So for the loop transformer, so for all the linear regression, depending on the linear coefficient, the number of loop iteration should be different, or is also the same?
Different depend on the what?
The linear coefficient of the linear regression model. So assume that the magnitude of the linear coefficient is very big. Would this also affect the number of loops?
Oh, okay, so that's another good question that we haven't investigated. Yeah, we just stick to the standard way of sampling the linear coefficients. So yeah. Thanks.
If there's no other questions, let's thank Liu Yang again for her great talk.
I don't think so.